Okay, in section 7.1 we just studied the exponential functions like b to the x and e to the 2x, and now we're going to want to start talking about their inverse functions like the natural log. But first we need to talk about inverse functions in general. Inverse function notation is very important to know. It's easily confused with reciprocating, so we have to be pretty clear on that. So for our inverse function notation, I use the notation f inverse of x to denote the inverse of the function f of x. Now, very important point here. F inverse of x does not mean to reciprocate f of x. So don't do that. F inverse of x does not mean to reciprocate there. Now, if f represents a function, oftentimes we use g to represent its inverse. So if you see functions running around like f and g, you know that g is the inverse of f, and we'll learn that pretty soon, vice versa, that g is the f is the inverse of g as well. Let's go ahead and look at properties of inverse functions. The first property of an inverse function is easy to write out, but sometimes it's a little bit hard to understand. So basically what this notation means is here the f inverse of a is equal to b. This means the domain of the inverse, if we switch over here, is equal to the range of the original function. So the meaning here is the domain and the range swap between a function and its inverse. So again, the domain of a function becomes the range of the inverse. The range of a function becomes the domain of the inverse, so I can swap the values for x and y. Another interesting property about inverses is that not all functions have an inverse. However, if a function does have an inverse, that inverse is unique. And of course, meaning that if an inverse exists, there's only one inverse that exists. Another interesting property of inverse functions is that if g is the inverse of f, then f is the inverse of g. And this makes sense because if a function has an inverse, that inverse would be the inverse of the original function. So if I have two functions, they're inverses of each other. Okay, not just one is the inverse of the other, but it goes either side there. If g is the inverse of f, then f is the inverse of g. The last property that we're going to look at has to do with a graphing property. The graph of a function and its inverse share a unique property. The graph of a function and its inverse reflect across the line y equal x. And we'll show this coming up here in a couple of examples. So those are some properties of inverses. Next, look at how to determine, or how do we determine if a function has an inverse. Now, not all functions have inverses. And of course, we know how to check to see if it's a function. We go ahead and give it the vertical line test. If it passes the vertical line test, we know it's a function. Let's go ahead and look to see how we determine if a function, we already know it's a function, has an inverse. Well, one way is to graph the function. So one way is to look at this graphically. So graph the function and see if it passes the horizontal line test. Now, just like the vertical line test, the horizontal line test works the same. Instead of holding your pencil or your chalk vertically to make sure it doesn't cross through more than one point at a time, we hold it horizontally and see if it doesn't pass through more than one point at a time. And we'll look at that graphically here in just a second. If a function passes the horizontal line test and the vertical line test, which it has to pass anyway to be called a function, that function is called one-to-one. So if a function is one-to-one, that means it passed both the horizontal line test and the vertical line test. So the important point here is that if it passes the horizontal line test, it has an inverse. So if it passes the horizontal line test, it has an inverse. Another way to determine if a function has an inverse is to use calculus. Now, both of these methods work equally well. The difficulty with the graphical approach is, unless you have a graphing calculator or Maple to help you out, it's difficult to determine the graph of a lot of functions. Calculus is really nice to use because all we basically need to do is to take a derivative. When we take a derivative, if that derivative is always positive, or if that derivative is always negative, that means that that function has an inverse. This is called monotonic increasing, because my first derivative is always positive. This is monotonic decreasing because it's always negative. So if I have a function that's constantly increasing, that means it will automatically pass the horizontal line test. If it's monotonic decreasing, the same thing will occur. So if I have a monotonic increasing or monotonic decreasing function, this implies that an inverse exists. Another way to look at this is to go ahead and take that first derivative again. And if we find the first derivative, and that first derivative does not have any critical numbers, that's basically saying that there's no local extrema, and that means it's one-to-one, which means an inverse exists again. So there's quite a few different ways that we can look at that. Let's go ahead and look at some basic graphs next. The first graph that we're going to look at, f of x, is an exponential graph. So we kind of recognize this graph from working yesterday. Let's see if I can get, here we go. This graph we looked at yesterday. So we kind of recognize this. This one not so much, but we'll talk about that in section 7.3. So this graph is my original function. This graph is denoted as my inverse. And note that they reflect across the line y equal x, just like we said. Now, let's go ahead and look at f of x first. The question is does it pass that horizontal line test? So to see if it passes the horizontal line test, we can see yes, it does. Passes a horizontal line test, therefore f of x has an inverse. Now, what about this function down here, f inverse of x? Does it pass the horizontal line test? Yep, so it has an inverse as well. And as it turns out, they're inverses of each other. Note also, and I kind of have the graphs marked up here a little bit, they all pass the vertical line test as well, individually.